Shall we start? Good evening, by the way, everyone. Let me share the presentation. Hope you can see the presentation.
Yes, sir.
Yes. Okay. Thank you. So, shall we proceed? Today, our topic is about statistics. I can remember at the very first session, someone asked a question that he or she has a statistical background and whether they can study or complete this course successfully or something like that. So now you would see even this within this course, the statistics and some mathematical concepts related to finance are discussed because even statistics, uh, sorry, even economics, what we discussed previously, you might see there are some mathematical and statistical concepts behind those things. So if whenever you have the analytical ability, these things you can cope with these things. Uh, Whatever your background, uh, it should be you should be able to grab these things and learn the content, understand the content. Um, but depending on your ability or the capacity, the time that you may have to devote may vary from person to person. So one thing is, as our course coordinator mentioned, it is very important to attend the class because I'm pretty sure you are very busy with the office works and your work life and your personal life. After the class, I don't know how much of time that you can devote to go through the either presentation or the course material or the course book uh, given to you. That there's a doubt on that. So therefore, at least if you can join and listen to the classroom and you have the flexibility to review the video, go through it again if possible. So you will get to know the subject and especially this statistics and the financial mathematics kind of things that we are going to discuss towards the latter part today. You need practice. You have to do some calculations, solve problems, and sums. Then you will understand the concepts much better. How the same concept can be tested in different angles and things like that. So just uh, whatever the examples that I'm going to discuss during the course, yes, uh, you can see the answer, you can see the method, how to derive the answer and things like that. But at the end, if you don't do it by yourself, it would be bit difficult for you. But if you do it by yourself, it will register in your mind and it will help you to have a better understanding. So with that, we'll move forward. The topic is statistics. What are the things that we have to discuss today? Okay. So basically, um, on statistics, we have two major topics: measures of central tendency and dispersion, then the diversification and correlation. So measure of central tendency is about calculation of mean, median, and mode. I hope at least you have heard those words. And the dispersion is how a data set distributed around that mean or the median or the mode. What is the spread? How do we measure those things? Quantify. Uh, that is about measures of dispersion. Then the diversification and correlation. This is again a mix of finance or portfolio management and statistical concept. Correlation is the statistical concept that gives you an indication about how two variables vary uh, together and with how what is the strength in that uh, variability. With that, we can have diversification in a portfolio. That means you invest in different assets. How that will help you to improve your risk return trade-off. That is about diversification. So those are the things that we are going to discuss today. So these are the key objectives under measures of central tendency and dispersion. So you should know about what is the arithmetic mean, geometric mean, median, and mode. So this may be examined by use of a simple calculation. So calculation. So at the end, you should be able to calculate arithmetic mean, geometric mean, median, and mode. Then uh, measures of dispersion, variance, again, two figures, sample variance and the population variance, then the standard deviation, again for the sample and the population, then the range. So again, it will be tested using simple calculation. So we will discuss all those things. What is the meaning of this and how do we calculate, and more importantly, when to use these measures. You may be able to do the calculation, but if you don't know when to use it and how to use it, that will be a problem. So even though it's not given here as an objective, I'm pretty sure you should know when you should use these measures. So why do we need statistics? Simply, we deal with data or information, especially in economics and investments. We deal with uh, numbers, maybe economic numbers, GDP figures, inflation figures, interest rates. Then on the other hand, from asset side, what are the returns of different assets? Maybe use historical data for up to 10 years or 5 years, all those data. So based using those data, we make some conclusions, inferences. That's what we call in statistical inferences. We draw inferences. You come to a conclusion. To come to a conclusion, we use statistics. Say, if you take the Sri Lankan population or all population in Sri Lanka, if you want to know about what is the income of a Sri Lanka, how do you measure it? Different, each and every person may have a different income. So how do you represent that in a single figure? So that is something that we use average or the mean income. You may remember we calculate something called per capita GDP. What is the GDP? per person. It is a kind of simple average. So instead of uh, taking the income of each and everyone, we use an average to represent the whole population. Likewise, if you take an investment, particular stock, what is the return of that stock? How do you calculate it? And how do you represent it? Maybe you may say over the last 10 years that stock produced average return of 20%, something like that. But does it mean each year it gives you 20%? No. Different years, the return may be different. But ultimately, we take an average and we say, on average, this is the return that we get. And we expect that will be the outcome into the future as well. So that's where we make the conclusion or the inference. Or at least what is the chance that a particular stock is giving uh, a return of 20%, minimum 20%, with a chance of more than 60%. So that type of things are the inferences or the conclusions that we made using data and statistics. We use it as a tool to draw conclusions. So for that, we need this basic statistics we call descriptive statistics. Descriptive statistics that, the term explained, that describe the data set that you have in two different ways. One is measure of central tendency. What would be the single figure that we can use to represent the whole data set? Or it may be considered as what is the midpoint of this data set. Then the measure of dispersion, but how far from that central point that this data can vary, spread over. So those are measured through the statistical concepts called variance and standard deviation. And the variance and standard deviation, in a way, both are the same. Only thing is standard deviation is the square root of the variance. So to measure the central tendency, we have the mean, median, and mode. So with that, we'll move into discuss each and every measure. What is the mean? So mean is the average value of all data given. Mean is the average value of all data given. How do we calculate it? And this is called the arithmetic mean as well. Arithmetic mean is the sum of all the observed values. If you have 100 values observed, add them together and divide by the number of observed values. That means 100. The total divide by the number of observations that we have, then we'll get the arithmetic mean. In mathematically, or using algebraic notation, it is written as this, what this sigma or the summation mark represents. That tells you add whatever the values, each and every value, add them together and divide by the number. How many observations? Then you will get the arithmetic mean. This x bar is the standard notation we use to represent the arithmetic mean. So we'll take a simple example. Assume you observe these values 10, 21, 18, 7, 14, 13, 19, 12, 9, 6. What is the average arithmetic mean of these numbers? what do you have to do? Add them together. 10 plus, 21 plus, 18 plus, 7 plus, likewise. Add them together and divide that total by the number of observations. How many numbers are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers are there. So add all those numbers, divide it by the number of observations. In this case, 10. There are 10 numbers. So once you add it, you will get 129. Divided it by 10, the answer is 12.9. So this is the arithmetic mean. That's how we calculate it. For any data set, if you have the raw data, that means individual observation, this is the way. Nowadays, with the computation power that we have, or the software we have, we can straight away calculate the average or the arithmetic mean using this method. Yeah, there are ways that you can group data into different classes and count the number of observations fall into that groups, then calculate the mean. Yes, that is also there, but yeah, we are not going to discuss that one because with the computation power nowadays we may not have to use those methods unless there's a specific requirement to do categorize the observation that we have. Because once we categorize observation, we lose some information. But here you get everything, whatever the actual observed values included in this calculation. So we'll get a much more precise answer. So 12.9, what does it mean? So on average, the value of this is 12.9. Then remember other thing. What is the maximum value of these numbers? What is the maximum value? It is 21. What is the minimum value? That is 6. This is the maximum value. This is the minimum value. The average is 12.9. Remember, the average should fall within the minimum and maximum. It can't go above the maximum or below the minimum. But say this is 6, this is 21. Where would this average fall? That depends on the numbers that we have. So basically, or in simple, these numbers are sort of distributed fairly throughout this range from 6 to 21. So therefore, we expect the mean to be somewhere in the middle, but in this case, there are a few numbers towards close to 10, 14, 13, 12. So that's why average comes as 12.9. And remember, other thing, this arithmetic mean may have an impacted or will get an impacted by the outliers. Say, if I add another number here, 50, what would be the average? What would be the average? Can someone do the calculation and let me know?
It would be 179 divided by 11, which would be 16.27.
16.27.
27.
27. Yes. So now you can see the mean, which was somewhere here, now shifted to this side, closer to this. This is because of the impact of this large number. If there was another number somewhere here, the mean will shift towards that side. So if this number 50, if I increase that to 100, so the mean may fall above 21, somewhere here. So then you can see only one observation is above the mean, all other observations fall below the mean. That can happen because of this extreme number. So therefore, whenever you do a calculation, the arithmetic mean, you may have to think about whether to include that number or exclude that number in your real life analysis, because that will distort the picture. So you have to find out what are the reasons for this outlier, whether it's a possible one or a mistake or a extreme case. If it is an extreme event, to generalize it, it may not be a prudent action. So you may exclude that and take the numbers which are the results during a normal circumstances. So this is one of the drawbacks in the arithmetic mean or the uh, average. So extreme or the outliers will have an impact on the final outcome. However, remember the mean should fall within the minimum and the maximum of the number set. Is it clear? Or is it difficult, this calculation? May I move forward? So this is a real life example, sort of fatal accidents in airlines. So during a 17-year period, what are the number of fatal accidents per year? So within the first year, there were 4 accidents. Second year also 4 accidents. Third year also 4 accidents. Likewise, number of accidents occurred in each and every year for 17 years. So on average, how many accidents occurred per year? That is given by the mean. So if you ask to compute the mean, if you ask to answer that question, on average, what is the number of accidents that could occur during a year? How do you do that? Just calculate the arithmetic mean. And we assume that, so probably even the next year, that amount of accidents will occur. So to do the calculation, again, add these numbers together. We don't have to arrange it in a particular order or from the in the ascending order or the descending order. No need to do that. Just add the numbers and divided by the number of observations. We have 17 observations here. You get 3.58. So now the real uh, variable is number of accidents. Can it be decimals? Either 3 accidents or the 4 accidents. There can't be 3 accident and half of accident, something like that. No, you can't have that. But that's how. This is the number that we get 3.58 accidents during a year. So you may expect 3 to 4 accidents per year. So if you go through these numbers, you would see most of the years you can see 4 accidents. There are few exceptions. In the fourth year, only 1 accidents, and in this year there were 8 accidents. So on average, you may expect 3 to 4, 3 or 4 accidents per year. And remember, in this case, when you interpret the mean, you have to link it to the time period as well. Number of accidents per year. 3.58 is the mean accidents per year. In some instances, you may not need not to link it to a time frame, but in some cases, you may. Especially in investment, you may have to calculate the mean return or the average return. So, but return is a measure that we use for a period. Is it a 1 day return or a 1 year return or a 6 month return? So therefore, again, in those calculations also, you'll have to refer it to a time period. So I guess that would enough about the arithmetic mean. Very simple calculation at the given numbers and divide by the number of observations given, you will arrive the arithmetic mean. And again, you can check whether your calculation is correct. Whatever the answer should fall within the minimum and the maximum. But even an incorrect answer can fall into that. But you will have some idea about that, whether your answer is a possible correct answer. But if you get an answer more than 9 or less than 1, that give that that will tell you definitely that answer is wrong. So you can cross-check your answer up to some extent, comparing the mean figure that you get with the number set given. Then the next measure of central tendency is the median. What is that? The median gives you the middle point of the data set. What is the middle point of the data set? That means on that, once you arrange the data set in an ascending order or a descending order and get the median, 50% of the observation fall below the median figure, 50% of the observations fall above the median figure. So it is the middle man. How do you find it? Again, take this set of numbers. This is not in any particular order, the order that they observed. But the first thing what we have to do to calculate the median is arrange them in a order, generally in the ascending order. So the smallest number is 6, biggest number is 19. You arrange them. Then count the number of observations. How many observations there are? 3, 4, 5, 6, 7, 8, 9. We have 9 observations. Then what is the middle one? What is the middle one? So on the first place, we have number 6. On the second place, we have number 7. Third place, we have number 9 like. So what is the middle? Remove this one. Remove this.
12.
This one. This one. Likewise, if you do this, you will see The middle position is the fifth position. The corresponding value is 12. So the median is 12. That's how we find out the median. So we have 9 observations. Remove the lowest 4 numbers. Remove the largest 4 numbers. What is in the middle? That is the median. That's how we find the median. But the question comes, here you have odd number of observations, 9. Then you can find the exact middle point. But what if there are 10 numbers? I have it one more here. Now there are 10 numbers. Still, the first step that you have to do is arrange them in the uh, order, uh, increasing, ascending order. Now, if you put it, you can see there are 10. What is the middle? You remove the first 4, you remove the last 4, you are left with 2 in the middle. There's no one single point. Now what do? We take the average of these 2 numbers as the median. The fifth position we have 12. At the sixth place we have 13. Add them together, divide by 2. The answer is 12.5. So the median is 12.5. There are 50% of the observations below 12.5, 50% of the observation above 12.5. So what is 50% of 10? 5. You can see 12.5 is here. So 5 observations are less than 12.5. 5 observations are more than 12.5. Even in the previous case, it is same. Out of 9, 4, 4. So this is exactly the middle point. So that is median. Is it clear?
Yes, sir.
Yes, sir.
So hope these are not these difficult calculations. So these two are like rules. You don't have to remember this as it is if you have got the concept in the previous 2 examples. So when there is an odd number of observations, find the middle term of the ordered data set. That means the value of the n plus 1 divided by 2 terms. So in the previous example, we had 9 observations. Plus 1, you get 10. Divide by 2, you get 5. What is the number in the fifth place? That is the median. But when there is an even number of observations, you can't do that because n divided or n plus 1 divided by 2, it would become 5.5. There were 10 observations, it would become 5.5. There's no position called 5.5. Then what do you have to do? Take the number in the fifth place, take the number in the sixth place, take the average of those 2. Then you will get the median. So what we did earlier is given here in a text form. If you want to remember, or in a as a rule, if you want, but not necessarily, get the understanding of what is median and you can do the calculation. Then the third measure of the central tendency is the mode. That is the most frequently occurring value in a data set. So the same number may be repeated in a data set, but different numbers, the frequency that appear in may be different. What is the number appears mostly? That is we call the mode. So you have 20 observations. What is the mode? That means what is the number that appears mostly in this data set. So one way you can do, list the numbers, say for 14.25 and count how many times. So 14.25, 1, 19, 1, 11 you see the first time, 28 for the first time, 24 for the first time, 23 for the first time, 14, 3 for the first time, but 19 for the second time. You can proceed. 27 first time, 25 first time, 15 first time, 7 first time, 34.2 first time, 15.5 first time, but 15 for the second time, 22 for the first time, 19 you have 27 for the second time, 21 for the first time. So you can see 19 appears 4 times in that data set, and the second highest is 15 and 27. All others appears only 1 time. So the mode is 19. So that's how we find the mode. Indeed, there's no calculation per se to do this. Just count the number that a particular or the occurrences of a particular number. We call it the frequency. So frequency of 19 is appearing is 4. Frequency of appearing 15 is 2. Likewise. So the mode is 19. So 3 different figures to measure the central tendency. And when are we going to use these 3 different figures? That's the next concern. What are the drawbacks of these measures? Drawbacks and the advantages. Okay, so far, do you have any question on these? How to calculate mean, how to find the median, how to find the mode. I would like to say find median and find mode rather than saying calculation. But the mean is a calculation, yes. Any question? Okay, if not, in the mode we have another concern or few concerns. Say in this all the numbers appeared only once, then what would happen? If the number appears only once, no repeated observation, then what would happen? There won't be a mode for that data set. So there can be instances there is no mode for that data set. And on the other hand, there can be ties. That means two numbers appeared with the same frequency. Say in this example, 19 appears 4 times. Assume 19, these figures were not there. Then what would happen? You can see 15 appears 2 times, 27 also appears 2 times. Then what is the mode? Both 15 and 27. Both appears 2 times. That's the highest number of occurrences. So in that case, when there's a tie, we call it it's a bimodal distribution. That means there are 2 modes in that data set. Similarly, there can be more than 2 modes. Whenever there are 3 modes, we call it trimodal. Beyond that, we call multimodal distribution or having more than 3 modes. But in some instances, whenever the distribution has even 3 modes, we call it multimodal distribution. That means having more than 2 modes. That means more than 2 numbers appears with the same frequency within that data set. Then there are more than 2 modes. So that's another problem when we use the mode. So the question is which measure to use. Whenever you have numbers, or most of the cases, whenever you have numbers, we use mean. We prefer to use the mean. We can calculate the average. Add the numbers together and divide it by the number of observations. So mean is the most commonly used measure. But not that all time you can use the mean. There may not be a meaning for that. We'll discuss that later in a minute. And the problem of the mean is the outliers, as I explained earlier. Whenever there's an outlier, that will influence the result. Mean figure will drag towards the outlier figure. So that may distort the picture. So whenever we get a data set, the first thing is try to find out whether there is any outliers. It may be one or more than one. Most of the data cluttered towards a one range, and there are few observations far away from the other observations. Those we can consider as outliers. Then we have to think about it, whether we are going to use it or not. You may have to find out what are the reasons for occurring these outliers. It may be an observation recording it may be an error, recording error. When you observe, say instead of 6, you wrote 60, something like that. That can happen. So, or it may be actual figure, but because of extreme event occurred, the observed figure is too high or too low. That's the problem with the mean. Then, however, mean is the mostly common used measure. Then the next one is the median. Median is mostly used when there are extreme outliers, as we discussed in the mean. To sort out that problem with the mean, use of mean when there are outliers, we may tend to use median. So we call them having a skewed data. That means some data towards one side of the observation, far away from the other. And the third one, mode, is used. The problem is there may be no mode or maybe have multi-mode model. But this is useful when you have a categorical data. You don't have the numbers, but you have the categorical data. What do you mean by categorical data? What's a categorical data? So say male, female, just two categories. Can we compare them? One is higher than the other? No. That type of data we call categorical data. Say you want to do a market research on the customer's preference on a color. So you are going to produce a shirt, garment. You want to know what is the color the most people would like to have. So the color, red, blue, green, yellow, whatever the colors. So those are categories. Then what you can do, count the number of people who prefer red, count the number of people who prefer yellow, likewise. Then what is the mode? Which color is preferred by more people? So mode would be red or the blue. It's not the number, it is the category. So to analyze that kind of data, we use mode. Is it clear? So those are the drawbacks or the negative points in each measure. And when are we going to use these things? When are we going to use mean? When are we going to use median? And when are we going to use? So most of the time, whenever we have numbers, we prefer to calculate the mean. But if the data are skewed, that means there are extreme values, then mean may not be a good representation. Then the median would be a much preferred measure. Even with the numbers, sometimes we prefer to use mode. But whenever we have categorical data, we have to use mode because we can't calculate the average of colors or good or bad or a smoker and a non-smoker, that type of categories. We can't do that. So definitely we'll have to use this categorical. We have to use mode to analyze those categorical data. Then the other mean is the geometric mean. In the arithmetic mean, what we did, we add the numbers together and divide by the number of observations. To calculate the geometric mean, instead of adding or calculating the total, what we do, we multiply each and every number. Then take the nth root of the multiplication. Nth root of the multiplication. So m1, m2, m3, mn are different numbers. We multiplied them together. So there are n number of observations. Therefore, we take the nth. That is geometric mean. So if we use the same set of numbers we use to calculate the arithmetic mean. To calculate the geometric mean, what do? We multiply 10 into 21 into 18 into 7 into 14 likewise and get the 10th root. The answer would be 11.9. So you can see this is bit close to 12.50, that figure, what the arithmetic mean we had. This is how we calculate geometric mean. I suppose this is also a simple calculation, but remember the calculator that you are going to use, you will have to practice it. In different calculators, you may have to key this in different ways. So practice your calculator. So this is an practical example that we have, especially in the finance, the use of geometric mean. Assume that you make a deposit of 50,000 rupees, which will earn 10% in the first year, 9% in the second year, 11% in the third year, and the 12% in the fourth year. And assume that you don't take out the interest at the end of each year. You reinvest that interest with the principal amount for the next year. Then what is your average return? How do you calculate it? Is it just the simple average? Oh, that means the arithmetic average. 10 plus 9 plus 11 plus 12 divided by 4. Is it the average return that you earn? So let's see. If we calculate the geometric mean, but here only thing is, whenever we have these numbers, to calculate the geometric mean, we have to use 1 plus the interest rate, because that is the numbers we have at the end, not the simple rate. So we calculate the geometric mean of these numbers. 1.1, that means 1 plus 10%, 1.1, 1 plus 9%, 1.09, 1 plus 11%, 1.11, 1 plus 12%, 1.1. We have 4 observations. When you calculate that, you will get a geometric mean of 1.10494343. But to get the average return, again, you have to subtract the one that we added. So the average return would be 10.494343. This is the average return. How do you check whether this is the correct average return? Okay, we'll do a simple calculation and see what is the total amount or the total interest that you get at the end. Total amount that you get at the end. At the beginning of the first year, we had 50,000 rupees. At the beginning, we had 50,000 rupees. We invested it at 10%. At the end of the first year, we earn an interest of 5,000. 50% into 10%, you get 5,000. Then end year balance is 55,000, which we will invest into the second year. So principal amount for the second year at the beginning of the second year is 55,000. Interest rate for the second year is 9%. Calculate the interest, you get 4,950. Now, what's the total balance that we have at the end? 55,000 plus 4,950. 59,950. Likewise, do the calculation until the end of the fourth year. At the end of fourth year, your balance is 74,529.84. So you can see, once we multiply this beginning figure with the geometric mean, but into the power 4, you get the exact same number. But remember, that depends on how many decimals that you use here. If you stop somewhere here, 1.105 rounded off, then your answer may be slightly different, but you should get a close answer. So this is the geometric mean. We use geometric mean to calculate the average return and the growth rate and things like that. So to calculate the average growth rate, average portfolio returns and things like that, we use the geometric mean instead of the arithmetic mean, because this gives you a much better picture. If you do the arithmetic mean in this example, you will get an answer, say 10, 19, 11, 30, 42, 42 divided by 4, you get 10 point something. Still, you get 10 point something. But you won't get the final outcome if you calculate the interest at 10.05. However, depending on the numbers that you have, arithmetic mean and the geometric mean would be much closer. But as a rule, however, how close it doesn't matter. Geometric mean is always lower than the arithmetic mean. Maybe even at a 10th of 15th decimal place, geometric mean is lower than the arithmetic mean. That is something that you have to remember. Comparison. So that's all about central tendency, measures of central tendency, arithmetic mean for the simple average, for the mean, then the median, the midpoint, and the mode, that is the most frequently observed value. It's not the number of, it's not the frequency, mode is not the frequency, but what is the number that you observe most frequently? That is the mode. Then finally, geometric mean. So now we know how to calculate those things and when to use these numbers. Then before we move into discussion on dispersion, measure of dispersion, I want to discuss about this quartiles, because one of the measures that we use to measure the dispersion is interquartile range. To calculate interquartile range, you should know about what is a quartile. So there's another term called percentile as well. I'm not going to discuss that, but the concept is the same. Say, what is percentile means? You split the range of the observed value into 1 over 100, 1%. And what is the value that observed? Below that, there is only 1% of your observations. In that, median is, I explained, median is the number or the midpoint of the data set where 50% of the observations fall below that, 50% of the observations fall above that. So that is the 50th percentile point in that terms. That is the median. In terms of quartiles, that is the second quartiles. So in quartiles, what we do, we split the data set into 4 equal parts. We divide the data set into 4 equal parts. But remember again, you will do that once you arrange that in the ascending order. To calculate the quartile or the percentile, you have to arrange them in the ascending order. Then only you can calculate the percentile or the quartiles, even the median. Median is the 50th percentile or the second quartile. So first quartile is the value at the 25th percentile point. That means 1/4 of the observation. What is the position of the 1/4 of the observations? What is the value of that position? Q2 or the second quartile is the 50th percentile point or the middle point. Then third quartile is the 75th percentile or 3/4 of the observations. Where the what is the observation which lies on the 3/4 of the observations? So like the same way that we did to calculate the median, first we have to arrange them in the ascending order, then find the corresponding position and find the value of that position. Or on the other hand, Q1, we can consider Q1 or the first quartile as the median of the first 50% of the observation. Median of the first 50% of the observation. And Q3 can be considered as the median of the second 50% of the observations. So we will go through an example. So this number set is given in the order, already arranged in the ascending order to make it simple. So what is the median? How many observations are there? 4, 5, 6, 7. There are 8 observations. Then where is the median? You don't have the single midpoint. It would be in between 4th and 5th observation. So median falls somewhere here. That is the average of 116 and 121. That is the median and it is the second quartile. The answer is 118.5. Now you have divided the data set into 2 halves. In the first half, you have 4 observations. In the second half, you have second observation. What is the median of these 4 observations? Again, you have 4 observations. There's no particular midpoint. It will be somewhere here. That is the first quartile. How do you find it? It is the average between 109 and average of 109 and 140. So the average figure is 111.1. That is the first quartile. What is the third quartile? It will be somewhere here in between 6th and 7th position. The average of 122 and 125. The third quartile is 123.5. That's how we calculate quartiles. Almost similar to the calculation of median. First find the median, take the lower half, find the median, that's Q1. Take the second half of the observations, find the median of that set, that is Q3. Clear? Any question? Then You see, you observe something like this. Q1, Q2, Q3. The distance between Q1 and Q2 are almost same as the distance between N Q3. What you can infer, the data is spread evenly, more even, or we call it symmetric. The number of observations in between Q and Q2 and the Q2, Q3 are almost same. But there can be instances Q2 is somewhere here. Then what is it? So 25% of the observations are concentrated into a small range. Next 25% of observations are distributed throughout a long range. So that there are skewed data. This give an indication about the skewness. We will discuss that concept later, skewness, but this gives you some indication. On the other hand, it may be other way around. Q3 and Q2 are much closer. So third 25% of the observations are concentrated into a small range. The second 25% of the observations are distributed in a fairly big range. So again, data are skewed into this area. It is also, there are extreme values here. That's why. That's why you can observe this type of either one. We call this as the box plot. You can get some idea about the shape of the distribution of the observation through that. However, this is not a part of this curriculum, but it's better to know these things in practice. Then we'll move into the discussion on the measures of dispersion. That means how far the data distributed from the midpoint or the central tendency measure. Most commonly used ones are variance and the standard deviation that is related to the mean. We measure that relative to mean. The others are range and interquartile range. Those are related to not necessarily to mean, but interquartile is related to the median. So we'll go through each and every measure. Range is the simple measure. As I mentioned, variance and standard deviation, it's about how far the observations can go above or below the mean. Interquartile range is about what is the distance between first quartile and the second quartile. So it basically it measures the variability of a data set. If you take the range, it is the simplest measure. It gives you the difference between highest value and the What is the full range of the observed data? So if that range is small, then you can infer most of the observations or observations are all within a small area. If the range is large, so the dispersion is very high. Observations are scattered over a big range. The same data set that we use to calculate the mode. What is the range? What is the minimum figure here? What is the maximum number? Minimum is 7 and the maximum is 43.25. So the range is highest minus lowest. 43.25 minus 7, 36.25. So the data distributed within a range of 36. And whether this is big or small, that depends on the numbers that you have. With this full numbers, 36 may be a big range. But if it is in thousands, even the range is 36, it not be a big number or a big range. Say 1000 to 1036. The range is small compared to the observed values. If it is decimals, even 0.5 may be a big range. So then again, whenever you use the range, you have to think about what are the units of measures and the size of the numbers that we use to decide whether the range is high or low. However, it is very simple to calculate the range. That's the difference between highest observed value and it is the difference between highest observed value and the lowest observed value. Then again, that can be distorted by extreme values. If there was something like 100, just one observation, 100, then what would happen to the range? 100 minus 7. The range is 93. But out of 21 observations, 20 observations falls within 36.25. The other one is in the far end. So that can distort the figure or the picture that you see. That's why in some or more some cases, not that any of these measures is the best. You may have to calculate 2-3 measures and see what gives the best picture. And that depends on your objective as well. When are you going to, or what is your intention? What are you going to do? What sort of data that you have? Then the next measure is the interquartile range. So as I mentioned, that's why I explained interquartile. Sorry, what is a quartile earlier? Because the interquartile range is the difference between third quartile and the first quartile. That is the difference between the third quartile and the first quartile. Whenever the data set is given, you have to calculate Q1 and Q3. So for this given data set, we have already done that. To calculate the interquartile range, what we have to do, take the difference between Q3 and Q1. So in this case, 123.5 minus 111.5. The range is, interquartile range is 12. Then again, whether this is a big range or a small range, that is relative to the number set that you have. With these numbers, 12, you may see it's not a big range. Then we'll move into the other measures, variance. This is a very important measure and again, one of the mostly used measure. Indeed, maybe the mostly used measure is the standard deviation, but to calculate the standard deviation, we should know the variance. It is the square deviations about the mean of a set of values. What does it mean? We take each and every, first we calculate the arithmetic mean of the observations. We calculate the arithmetic mean of the observation, then calculate the distance of each and every observation from that mean. Calculate the distance of each and every observation from the mean. So that means observation minus the mean that we calculate. Then that difference is squared. You know what does it mean by square? What does it mean by x squared? What does it mean by x squared? That is the multiplication of a number by itself. Multiply x by x, that is x squared. So here what we do, we calculate the distance and multiply that distance by the same. Then you get a x squared. For each and every observation, you get that square deviation. Then calculate the average of those square deviations. Total them and divide by the number of observations. But if you divide it by the number of observation, that will give you the population variance. If you divide it by the n minus 1, that means one less from the observed numbers or the number of observations, that will give you the sample variance. But remember, same data set, you divide it by n, you get the population variance. You divide it by n minus 1, you get sample variance. No, it won't happen. First, you have to decide whether you are going to calculate the population variance or the sample variance. What is the data set that you have in your hand? So for that, first we'll have to understand what is population, what is a sample. What's the population? What's the population of Sri Lanka? What does it mean? Each and everyone who's living in Sri Lanka counted into the population. Each and everyone who is in Sri Lanka is counted into the population. So that's the population. Say, if we take this class, if we take our class, it is mentioned that there are about 25 students who are registered. That is the population of this class, 25. That is the population. Say, you want to do a study about the age of that population, then you have to find out the age of each and every student in this class. So you should have 25 observations, 25 numbers, age numbers. You sum them up, divide by 25, you get the average age of the whole population. But today, now, there are only 20 participants in this class. We can consider it as a sample of that population. To represent the population, we take only few of that population. So if we take that today's participant, that will reflect the that can be considered as a sample. get that age of those 20, divide it by 20 at those ages, divide it by 20, we'll get the sample mean. But we assume that reflects the average age of the total class. So likewise, when it comes to the variance, first we have to identify whether we have the observations of the whole population. The population that depends on your problem. That depends on your problem. Say, you want to calculate the average return of the stock market, then you have to get the return of each and every shares in the market. That is your population. That is your population. But you don't want to do that. You just take a sample, only, say select only 50 shares, calculate the average. You assume that average will represent the whole market. That is the sum. So is it clear the difference between population and sample?
Can you please explain again, taking that classroom example, population
Yes.
variance and sample variance once again? Thank you.
Yeah. Now, before we move into the variance, first we have to understand what is the population and what is the sum. If we take our class, it is said that there are 25 students registered into the this class. So our population, class population is 25. That is the population. That means whatever the problem we have, whatever the scope, each and every unit that fall into that scope, we have to count. So in our class example, all 25 students represent the population. But now we have only 20 students in the today's class. That can be considered as a sample of students of our class. Out of 25, we have considered 20. That's a sample. Is it clear?
Yes, it's clear. It's clear.
So, yeah, say, like we have about 200 or whatever the number of shares in our stock market. That is our population. If you want to replicate our stock market, population is whatever the listed shares, each and every share. Say there are 200 shares listed. So 200 shares are the population. But you select only 50 out of those 200, whatever the method that you use, you select only 50 shares. That is a sample. You select 50 shares. I also select 50 shares. That may be completely two different set of shares. Oh, there may be some common shares, but we consider them as two different samples. So you can draw many samples from the same population. Is it clear?
Yes, well understood. Thank you.
Then you want to calculate the variance. Assume you have the observations about the whole population. So in our class, we have 25 students. We have the age of each and every student. Then we can calculate the mean of each and every, mean of the students. That is the population mean. Then what we do, take the first student, what is his age, subtract the average, square it. Likewise, we can calculate 25 square deviations. Divided by 25, then we get the population variance. Variance of the whole population. To calculate that, we need observations on the whole population. Is it clear? To calculate the population variance in our class, say age, what is the variance of age? to calculate that, we should know age of each and every student in the class, 25 students. Then only we can calculate the population variance. If we have 25 observations, we do this calculation, you get the population variance. But say I just take the 20 students who is participating today, then do the calculation, calculate the average, and calculate the square deviation, sum them up and divide it by 19 because there are 20 students today. N minus 1 is 19. That will give me the sample variance. What is the variance of that sample? That is the difference. Is it clear?
It's clear. So the N stands for either the number of we use in the population, or it might differ. It will definitely differ in case of the sample. Thank you.
N is the number of observation. N is the number of observation. Whether it's in the population or sample, it doesn't matter. But through the problem, you should know whether you use the data of the whole population or only a part of the population. If it is part of the population, that is a sample, then you have to divide it by N minus 1. If you have all the observations about the portfolio, then you divide it by N. Clear? Is it clear?
Yes, it's clear. It's clear.
So we'll do an example. This is the same set that we have 100, 609, that set of numbers. First, we have to calculate the mean. Here we assume this is the population. There are only 8 people, say 8 students in a class, and this is height in centimeters. What is the average height? So add them together, divided by 8. This is the average height of the students in that class population. Assume there are only 8 students in that class. Then we want to calculate the variance of the height. Then what do we do? Take each and every observation. First one is 106. 106 minus the calculated mean. 106 minus 117.5 and square it. You get 138.062. Take the second observation, 109. Subtract the mean, 109 minus 117.5, square it, you get 76.562. So for each and every figure or the observation, you do this calculation, then you get the sum is 439.5. So you add these figures. This is the total of squared deviations, 439.5. Then what do we do? To calculate the population variance, we divide this 143.9.5 by 8. We get 54.937. That is the population variance. But assume we have a class of class with the students, 40 students. There are 40 students in the class, but we picked 8 students. The height of those 8 students are given here. Then what is this? This is a sum. Then this is a sample. But we do the same calculation. The method won't change up to this point. You calculate the mean. This is sample mean, then 117.75 is the sample mean. And this is the sum of square deviation. in the sample, then the variance would be that sum of square deviation divided by 7. That is 62.7857. Sample variance is higher than the population variance generally, because you don't take the whole observation, each and every one. You take only part of. Is it clear? Even though I use the same set of numbers with two different assumptions or scenarios. In the first instance, I assume there are only 8 students in the class, and these are the heights of the students in centimeters. For the calculation of sample variance, I assume there are 40 students in the class, but we took 8 students. We selected 8 students and measure the height of those 8 students in centimeters and did the calculation. Clear? So therefore, whether it's a population variance or the sample variance, it doesn't depend on the numbers. It depends on the situation or the problem. Whether you have taken a sample or whether you have considered the whole population. Is it clear?
Clear.
So remember the story. In the first instance, in the class there are only 8 students. In this one, in the class there are only 8 students. But in this case, there are 40 students in the class, but we took only 8 students to represent the whole population. Say, you want to calculate or do a study about the income of Sri Lankan population. Practically, can you observe the income of each and every person in the country? You can't. Then what do? You may select, depending on the possibility, few thousands of people and observe their income, then calculate the mean and the variance and things like that. You use the sample to represent the whole population. Got it? It's like when you cook, you want to check the salt level in that curry. Do you eat the whole lot? No, you just take a small bit and taste it. That the small bit that you took is the sample. Everything in the container, it is the population. Is it clear? So
In this
every day we do sampling.
in your first scenario, you said there are 8 students in the class, and if we are going to apply sample variance for that same thing, say take 5 students, we need to recalculate the mean and
Yes.
then
Say you out of 8 you took 5 students. 1, 2, 3, 4, 5. These only these 5 students. Then you have to calculate the mean of these 5 observations. Then calculate the square deviations and divide it by 4. Got it?
Why do you divide it by 4 when there is 5 that you're taking for the sample?
Yeah, there's a concept called degrees of freedom, especially in a sample. If you know the sample mean and you know the observations of say this, consider this 8, you know 7 observations and you know the mean as well, then you can calculate this last observation. Because mean multiplied by 8, you will get the total. Then you subtract the total of these, you can get this. That's the simple explanation. So to give a leeway for that, you divide it by n minus 1. Or in other one in a sample, you said whenever you have observations like 5, 1, 2, 3, 4, 5, you have only 4 caps. That's another explanation. Don't worry too much about it. You need to have a bit deep understanding about statistics to understand that difference. We call it the degrees of freedom.
Thank you, sir.
But again, remember, when the sample size is very big, say 100,000 minus 1 may not give a big impact. So when sample size increases, it get closer to the population. So therefore, whether you use n or n minus 1, it won't give a big difference. So and remember, the statistics, it won't give you perfect answers. It's like estimate, and it's not the sample variance 62.7857. If you take another eight student as the sample from the same set of 40, you might get a different mean, different sample variance. Based on that, you made conclusion. Got it? So this is not the only, or the variance is, this is not a fixed. But if you take the population variance, whoever who does the study, if they measure the height properly, everyone should get the same mean and same variance. Is it clear? Because it's the population. Everyone is counted. Everyone is represented in there. But in a sample, depending on the sample that you take, the outcome may differ. But we assume that represent the whole population.
So one question,
Yes.
just a matter of calculating the variance. What is actually does variance means in a set of data set? Let's say a series of product
Yes.
weights
Yes.
like much.
It's very easy to explain it once we discuss about standard deviation. I'll
Okay.
explain it. Yeah, it is easy. Is this clear? How to calculate the variance?
Yes, sure.
So then if we move into the standard deviation, it is nothing but the square root of the variance. It is the square root of the variance. Then again, we have a population standard deviation and the sample standard deviation. So this is population standard deviation. You can see within the square root, we have the variance. Here also within the square root, we have the variance, but this is the sample variance. It is divided by n minus 1. Here it is the population standard deviation. So that's it. Then what does it? Okay, we'll do the calculation as well. So this is the population standard deviation, 439.5 divided by 8. Take the square root, 7.412. In other words, whatever the 54.9375, you take the square root, you get 7.412 for the sample standard deviation, whatever that 65 something, take the square root, you get 7.9237. So what does it mean? So that represents the average amount by which the values in the distribution deviate from the mean. What is the average value that deviate from the mean? And this will give you a much better picture. Here, this is, however, this is an extreme. This is, however, an extreme, that normal distribution. That means observations, our observations are distributed in a symmetrical manner like this. So what is this height? You can simply assume that is the number of observations that we have at this. Say, if this is that 126, how many students with the height of 126, likewise. So what does it mean? The standard deviation, this is the mean figure. So observations can deviate from this mean. If it is by one standard deviation, that means from mean minus, what is the figure? 7.9, and mean plus 7.12. So in our example, 117.75 plus 7.92. What is the proportion of observations that we can observe within that range? That depends on the distribution that we have, but in simple terms, in a normal distribution, we can approximately get that figure. So this is the mean figure minus one standard deviation, mean figure plus one standard deviation. Within that area, we will see 68% of the observations spread around that. In our example, in the previous one, if I take it as 117 is the mean, forget about the decimal, minus 7. And 117 plus 7. That means 110 to 124. In between the range of numbers 110 to 124, we will see 68% of the observations fall within that range. That's how we interpret standard deviation. Is it clear? But this is only for the normal distribution. For others, that percentages may vary, but again, don't worry about those. But only thing is, if the variance is high or the standard deviation is high, what you can expect, there can be observations far away from the mean. Either up or down. Is it clear? If the standard deviation or the variance is high, you would expect to observe figures far away from the mean. So the deviation is high. That's why we call it measure of dispersion. If the variance or the standard deviation is low, that we can expect observations to fall within a very narrow range. Then again, whether the range is too big or too small, that depends on the numbers that you have. Is it clear? You got some idea about, got an answer for your question? How
Yes,
to interpret this standard deviation?
one following up question about this one. So let's say this 117 is like market price of an asset. So let's say the standard deviation is like 7. So which means going minus standard deviation, like the market price of this asset is undervalued. So then with time, which will return to its original price. So is it something that this standard deviation is mentioning?
Uh,
Actually application of
The-
this standard
no,
standard deviation.
say, what you say is the market price. So
Yeah.
why do you have a distribution in the market price? In different times, it has different prices. So the distribution is like this. Yes, in a way you can see when the market is now it as 110, that means one standard deviation below the mean. If we assume the market follows that central tendency or move towards the median, yes, if you assume that, you can expect the market will go back to, or the market price will go back to 110. That means it is undervalued. Or if the market is now at 124, you can think, yes, it is overvalued and it will come back to 110. But for that, you not necessarily have that standard deviation. Even somewhere here, say 117, now you observe it as 115. If you still expect that will go towards the mean, then you can think it as undervalued. It's not necessarily the standard deviation, but yes, we use these standard deviations to guide that. May not be one standard deviation you consider it as undervalued, but definitely when it goes below 2 standard deviation or 3 standard deviation, it is sort of extreme. Got it?
More likely to 80 to 20 is somewhat we consider extreme, right?
Yes. Then you would expect it will come back, say, because 68% chance is their price to fall between 110 and 124. Correct? There's a 68% chance the price would fall between 110 and 124. Now the price is 100. So the chance likelihood is high, the price to go up and fall into this area. If the price is somewhere 150, there's a possibility that price will go down and fall into between this 110 and 120. That's the guidance you can get it through this. Got it?
Yes, clear. Thank you.
Yeah. When we discuss about technical analysis, we use this concept. Yes. These bands and two standard deviations and 3 standard deviations. When we discuss about mean reversion, I hope it is there in the technical analysis. Is it clear? But remember that 68%, that is valid only for the normal distribution. In that, it is a symmetrical distribution. That means observations are distributed symmetrically for the both sides from the mean. So therefore, in this, mean and the median and mode are the same. You can see highest frequency is at the same place. And 50% of the observations fall below this. And 50% of the observations fall above this figure, mean figure. So therefore, mean, median, mode are the same for a normal distribution. That's another thing that you have to remember. Is it clear? Any questions? sorry, we didn't take a break today. What do you think? Now, I don't think we have a time to take a break. Shall we continue? Is it okay? Shall we finish this? So then understanding about this is very important. As given in the picture, you can see 68% of the observations falls between mean minus 1 standard deviation and mean plus 1 standard. Then if you take the range mean minus 2 standard deviation plus mean plus 2 standard deviations, there will be 95% of the observations within that range. If we take the deviation of 3 standard deviations, approximately 99.7% of the observations falls within mean minus 3 standard deviations and mean plus 3 standard deviations. So these three figures very important to remember: 68%, 95%, and 99.7%. 1 standard deviation, 2 standard deviation, and 3 standard deviations. So that is we call the empirical rule. So distance from the mean and the values within that distance. Mu plus and minus sigma. Mu stands for the mean. Sigma stands for the standard deviation. So within this range, there will be 68% of the observations. Mu plus or minus 2 sigma, there will be 95% observations. Mu plus or minus 3 sigma, there will be 99.7% observations, approximately. So we can use those figures to do some approximations and get some inferences. So this is an example of how do we use it. A company produces a lightweight valve that is specified to weigh 1,365 grams. So forget about whatever the product. You don't want to know about the specification or the what is this. They produce something, the weight should be 1,365 grams. But due to several reasons in the manufacturing process, calibration of the machines and things, it may change. Raw material quality may change. Therefore, or the mix may slightly change. Therefore, they may not be able to produce whatever the goods in the exactly same weight, that 1,365 grams. It may vary. So they have observed that the production process produce the good with a mean of weight of 1,365. The mean is their target, but there is a standard deviation of 294 grams. Okay, then now they want to know, okay, if we take 95% of the production, what would be the weight range of these products? What would be the weight range of that products? How do we answer that question? We assume that the weights are normally distributed. So then we know that 95% falls within 95%, within plus or minus 2% standard, two times standard deviation. So the mean is given 1,365. Standard deviation is 294 grams. Then mean plus 2 standard deviations gives us 1,953. mu minus 2 sigma, or that means mean minus 2 standard deviations, gives us 777. That means 95% of the production, the weight of those production will range from 777 grams to 1953 grams. So this is the range applicable. So this is the outcome. So now you can decide whether we can tolerate that. The target desired level is 1365, but out of, if we take 95% of the production, there may be items which has a weight of 1953. Now you can decide whether it is acceptable at an acceptable level or not, or you need more precision and bring it or reduce the standard deviation, produce the goods much closer to the mean level or the target, or is this a acceptable range? That's how we use in the use these concepts in practice. Is it clear? We can ask another question on the different way. So approximately 16% of the weights would be more than one weight. If we take 16%, it is the weights of these that more than a value, that gives us 16% of the observations. So here we have to understand different percentages fall within different range. So in this picture, 0, it is not the 0, it is the mean, but 0 standard deviation. -1 is 1 standard deviation down, 2 standard deviations down, 3 standard deviations down. This side, 1 standard deviation up, 2 standard deviations up, 3 standard deviations. So what would be the percentage fall in this range? This yellow color range. What is the percentage? This is the mean. For a normal distribution, it is the median as well. So what is the percentage fall in this range?
50%?
50%. Yes, exactly. It is 50%. What would be the percentage that falls between this range? Mean to 1 standard deviation up.
Roughly about 16.33.
Yeah, it is. Because we mentioned minus, in between -1 and +1, we had 68%. -1 and +1. If we go back to this example, remember this range, it is 68%, but this is the midpoint. Then whatever the percentage here is same as the percentage here. That means 68% divided by 2, 34% falls into this range. Clear?
Very clear.
So the blue color range, it would represent 34% roughly. Then all together, up to this point, 50 plus 34, 84%. Then the white color range, that represents the highest, 16%. Then what should be the value here? It is the mean plus 1 standard deviation. Mean plus 1 standard deviation. So 16% of the production would have a weight more than 1659. Mean plus the standard deviation. That's the answer for this question. So likewise, there can be many questions on this range. Okay. On the other hand, the same question can be asked in a different. What is the percentage of the production of which the weight is less than 1659. What is the percentage of the production of which the weight is less than 1659? It is 84%. This represents 1659. So 84% of the production weight is less than 1659. So likewise, there can be different questions on this. So the key to answer that question is identifying different ranges, this empirical rule. Remember this empirical rule. Within one standard deviation, you will find 68% of the observation. Within two standard deviations, you will find 95% of observation. Within three standard deviations, you will find 99.7 observations. And the other thing is, it is symmetric around the mean. Is it clear? Any question on that? Then what we discuss about skewness. So in the normal distribution, which is in the middle, it's a symmetrical distribution. And remember that not that data in each and every instance or each and every example, each and every scenario, data will be distributed in a normal distribution. It won't happen practically. Practically, it won't happen. But if you have large number of observations, that can happen. We might have deviations. So positive skewed one and negative skewed one. Now here you can see most of the data is towards the left side of or the lower side, but still there are observations at the far end into the right side. This type of a shape or a distribution we call positively skewed. So there are observations to the far end of the right side or rightly skewed or positively skewed. The opposite is the negatively skewed. There are very small extreme observations in the distribution. Those are we call negative skewed. So the key is again for a normal distribution, mean, median, and mode would be the same. But for a positive skewed one, mean is higher than the median, which is higher than the mode. The reverse is true for a negative skewed one. Mean is the smallest, then the median, then the mode. If you observe mean, median, and mode, if they are not the same, at least very close, then you may guess whether it's negatively skewed or positively skewed. That skewness, it's about whether it follows the normal distribution or symmetrical distribution or not. And remember, not that each and every symmetrical distribution is a normal distribution. There can be other distributions which are symmetrical but not normal. So in this, that explains, we call that as the Curtises. So this is the normal distribution, which we have that 68% and 95% rule. But if we take this one, the peakness is high. This one, it's much more flatter than the normal distribution. So deviation from the normal distribution, when the peak is high, we call it as a positive Curtises or leptokurtic distribution. And when the curve is flat, we call it negative Curtises and or platykurtic distribution. So that again something that we have to remember, because if the distribution is bradycardic or leptocardic, then we cannot use that empirical rule. Especially in the negative cortices, you can see there are fat tails. The chances of occurring extreme values are high, either way. Negative side or the small side or the large side. But in these positive cortices, that chances are low. So there can be different distributions. There can be distributions, even the peak is high, but there can be extreme values as well. So it is possible. There are distributions like this. It goes like this. Peak is also high. Flat tails also possible. So whenever you make conclusions, you have to make sure about these fat tails, especially in the finance industry. Fat tails means extreme events. The probability of occurring extreme events is high compared to a normal distribution. That will give you a risk. That's the ultimate use of this concept, cortices and the skewness. See here, negatively skewed one, you can see more chances of occurring negative results. In a positively skewed distribution, you can expect more chances of occurring more positive outcomes. Say if this is return, if the return of an asset is positively skewed, that means there can be high chances of occurring high returns. But if the return is negatively skewed, there is a high chance of occurring large negative returns. So those are the things that you have to consider when you take decisions or making analysis. So I guess that's all about first topic, that means measure of central tendency and dispersion. So we have to discuss about diversification and covariance. But I guess we'll keep it for the next week since we didn't take a break as well. You must be tired and maybe overloaded. Depend on your background. So shall we stop here?
Yes, sir.
We'll continue the next day, no, sir?
Yes, it's better. No? Any questions before we stop here about what we discussed so far? So the first few things are, I think, very simple, straightforward calculation of mean, mode, and the median. Then even the calculation of range should be very straightforward. Interquartile, which may be a bit of issue, but if you know how to calculate the median, then it's not a big issue. Calculation of variance and the standard deviation. I showed you how to do it in the simple way. However, that's the way that you have to do. Calculate the mean, take the deviation from the mean, square it, sum them up, and divide it by the number of observations or number of observations less 1, depending on whether you use the population information or the population data or the sample data. Once you take the square root of it, that will give you the standard deviation. that gives you a measure of how far the observations can deviate from the mean. What is the proportion of observations that falls within certain ranges, especially in when the observations are distributed normally. Then the deviations from normal distribution, either through the skewness or kurtosis, weakness. And what would be the outcome? If the distribution is skewed, what would be the outcome? Or what are the things that you would expect? If the distribution is more peaked or flat, that means positive kurtosis or negative kurtosis. What are the outcomes, positive outcomes, and the consequences? So that's the summary what we discussed today. So we'll stop here. Now I feel we are behind 1 week. So we'll think about a way to catch it up. By today, we should have completed the economics and investment analysis. But we haven't touched the investment analysis, not even the economics one. We have to discuss about correlation and the diversification benefits, as well as financial mathematics, that is about calculation of present value and future value. So still we have to discuss those things. Then discuss about fundamental analysis and technical analysis. Hope we will be able to finish all those things within next week. Okay, then we'll stop here. Good night.
Thank you, sir. Good night. Good night, everyone.
Thank you, sir.
Good night.